Swayam Prabha. Digital India. Educated India.
Discrete log problem. So, discrete log problem is basically used in we have seen the Diffie-Hellman key exchange protocol, we have seen Elgamal crypto system. So, there we have seen the discrete log problem. So, what is a basically discrete log problem? We have given a group, G, which is basically a multiplicative group and which is a cyclic group, and A is a say alpha is a generator of this group. Alpha is a generator or the primitive element of this group. So, it is a cyclic group generated by alpha, primitive element of this group, and the discrete log problem is basically, so we choose, suppose the order of G is n, suppose order of G is n. So, that means we choose a from lies between 0 to n minus 1, and we compute beta, which is basically alpha to the power a. So, if it is multiplicative sense, then alpha into alpha a times, or it could be additive sense also. So, depending on the operator we are using. So, we compute b is equal to alpha to the power a. Now, the discrete log problem is basically what? Now, given this, given G alpha beta. So, these are known, given G alpha beta. So, what we need to calculate? We need to get A. So, that is the problem. So, find A. Find A. So, A is usually denoted by log of beta alpha like this. So, this is the discrete log sense. So, find A. So, this problem is called discrete log problem. So, given the instance G is the group, G must be known, alpha beta, alpha is the generator of the group or primitive element of the group, and beta is the alpha to the power a. So, given the value of beta, we need to calculate a. So, that is the discrete log problem. So, usually, so based on this discrete log problem, we know the Elgamal crypto system. So, basically for Elgamal crypto system, what we have? G is basically ZP. So, what is the Elgamal crypto system? So, Elgamal is basically we have Elgamal, in Elgamal crypto system. So, basically P is a prime, we are choosing P to be prime such that discrete log problem is hard. Problem in ZP star is hard, hard means intractable. So, there is no I mean it should be computationally hard. Okay. So, then say alpha is a generator, say. So, ZP is basically, ZP star is basically say generating by alpha, where alpha is a primitive element, and say order of the group is say order of the group is p minus 1. Now, what are the keys? So, Alice is communicating with Bob. So, this key generation algorithm. So, the Alice wants to send a message to Bob. So, this key generation is done by the Bob. So, what Bob is doing? So, Bob is having this group ZP star, and then Bob is choosing A. So, Bob is choosing A, which is basically secret key of Bob, and Bob is computing beta, which is basically alpha to the power a mod p. Okay. So, now this is basically this is secret and this is the public. So, the public key of Bob consists of beta and alpha and obviously P. So, the group must be known and then the secret key is A. So, what Alice will do? Alice wants to encrypt a message which is basically say M. So, Alice will generate the ciphertext which has two parts, y1 and y2. So, basically Alice will choose a k random number and then Alice will compute y1 equal to alpha to the power k and y2 is equal to m into beta to the power k. Okay. And then this is the encryption. This is the encryption. Encryption and what is the decryption? What Bob is doing? The decryption is basically Bob is just calculating y2 into y1 to the power a minus this. So, this should give us m. So, this is the decryption. Okay. This is the decryption. Decryption which is done by Bob. Okay. So, now the thing is if so to decrypt this Bob is using Bob's secret key. So, this is the secret to the Bob. Now, suppose if Oscar is knowing this A, then Oscar also can decrypt it. So, the Oscar, the attacker, so this is the public key. So, Oscar knows beta, Oscar knows alpha. So, if somehow Oscar knows A, then Oscar can decrypt it. So, that means to knowing A, Oscar has to, so beta is basically alpha to the power A. So, given these two, finding A is basically hard. So, this is basically discrete lock problem is hard. So, a security of Elgamal crypto system is based on the discrete lock problem hard. Now, we talk about how to what is the algorithm to finding the handle this problem discrete lock problem. Okay, so let us start with the exhaustive search for this problem. So, we will now talk about solving the discrete lock problem. So, the first approach we will do the exhaustive search. Exhaustive search or brute force method. So, what is the problem? So, we have a group G which is basically generated by alpha and the order of this group is say P and we have given a beta which is basically alpha to the power A where A is from P minus 1 and we need to, so this is known, this 2 is known and we need to, this 2 is known and from here we need to find this A. So, that is the problem, that is the discrete lock problem. Okay. So, how to find A? So, what is the exhaustive search method or exhaustive search? So, we know the A is from 0 to P minus 1. So, what we do? We will try for all possible A. So, we first choose some A. So, A is equal to 0 or A is equal to 1. So, we just do like this. So, alpha, alpha square, alpha cube, we keep on calculate this alpha to the power I like this and every time we try to match this with whether this is equal to beta or not question mark, whether this is equal to beta or not question mark. So, if this is beta then our k is our A is basically I. So, this is the exhaustive search or brute force attack. So, we keep on calculate alpha, alpha square, alpha cube like this and every time we check that alpha to the power k is beta or not. If suppose alpha to the power k is happen to be beta, then that means that k is our A. So, that is the exhaustive search, but this will take how many time? This will take order of if this is P, order of p times, I mean. Okay. Now, how we can fast this? So, this is a, we can make it faster by doing the table lookup. So, what we do? We just, if we have if we are allowed to do some p processing, so what we do? So, this is called table lookup. Table lookup method. So, what we do? We store the this pair I alpha to the power I. So, for all possible I. So, I is equal to 0, 1, 2 up to p minus 1. So, we store this in a table, store in a table with respect to we sort this basically, sort it with respect to the end point. This is the start point, this is the end point with respect to the end points. So, we can use any sorting algorithm to do that. Now, if it is sorted and we store, we maintain a table where we store this. Okay, so, now then we have given a beta, beta is basically alpha to the power a. Now, we have given beta. So, what we do? We search this beta into the table. So, these are sorted. Now, we can search using the binary search. So, since these are sorted, this search will take how much time? Logarithm time. So, we search it. Now, suppose it is matching with alpha to the power k. Now, this k is basically our a. So, if alpha to the power k is happen to be beta, this imply a is k. So, this is the table lookup method, but this will take the memory also, because we are going to store this all the tables in an array like this. Okay, so, another method is Shanks algorithm. So, these are the this is another method to finding the discrete log problem. Shanks algorithm. So, this is also taking G n alpha beta or G p, say p is the order of the group. Okay, if we take n is the order of the group. So, order of the group is n and alpha is the primitive element of the group and beta is basically alpha to the power a, and we need to find this a. So, this is the problem. Okay. So, this algorithm is telling is like this. So, we first store m is equal to root over of n, and then we compute for j is equal to 0 to m minus 1, do we compute this value. We compute alpha to the power m into j. So, alpha to the power m to the power j. So, alpha to the power m into j, and then we sort this. So, there are m ordered pair. We sort this m ordered pair. They are basically j comma alpha to the power m j. Okay, in a list L1. So, maybe in the sorted in sort with respect to the endpoint in the list L1. Now, also if we prepare a list, another list L2 like this. So, this is for I is equal to 0 to m minus 1. We compute this value beta into alpha to the power minus I, and this we store into a list L2 in a sorted way. We sort the m ordered pair, this m ordered pair so I comma beta alpha to the power minus I in L2. Okay. So, we have two ordered pair. Now, we have two lists where we are sorting this and this. Now, we match the endpoint, and suppose we find a pair. So, this is 8 Suppose we find a pair in the L1 and L2 also such that their endpoint is matching. Suppose we find a pair say j comma y in L1 and I comma y in L2 having the same y value, this same endpoints. Okay. Then that will give us, then our this log of beta alpha is basically mj plus I mod n. Okay, mj plus I mod n. So, why this is so? Because we know y is equal to, from the least one we know, from L1 we know y is equal to basically alpha to the power mj. So, if it is same as beta to the power beta into alpha to the power minus I. So, if this is also y, then basically what we have, we take this alpha this side, we have alpha to the power mj plus I is equal to beta. So, this implies this is our log of that. So, this implies log of beta alpha is equal to mj plus I. So, this is our A we are looking for. Okay. So, this is the correctness. So, we will take a quick example on this. So, let us take a quick example on this. So, suppose we want to calculate log of log 3 base 5 to 5 okay, in Z 809 and this is a multiplicative group. Okay. Now, 809 is a prime. So, this is our P and 3 is a primitive element in ZP. Primitive element in Z809 star. Okay. So, here alpha is 3, n is 808 basically p minus 1 and beta is basically 5 to 5. So, we need to find out A. So, we will just run that Sang's algorithm. So, for that we take the m which is basically square root of n 808 upper ceiling. So, this will give us the value 29. So, we compute alpha to the power m because we have to again compute alpha to the power m to the power j. So, we compute alpha to the power m. So, alpha to the power 29 which is mod 809 which will give us 19. So, now we first prepare the list L1. Okay. So, to prepare the list L1 we have to calculate this j m alpha to the power m into j basically. So, basically 99 to the power j mod 809. So, this is the values which will be stored in L1. So, if we do that, this is our L1. So, let us have the L1 and this is for j is equal to, j is from 0 less than equal to j less than equal to 28. Okay. So, if we just calculate this, let us quickly write that. So, 199, 293. So, we can just easily check this 308, 4,559, then 5,329 and basically dot 10 comma 644, then 11 comma 654. Anyway, one must calculate this dot dot dot, and the last one is 28 comma 81. So this is the list L1. Similarly, now we have to calculate the list L2. So how to get L2? To calculate L2, we need to do the beta into alpha to the power minus 1. So to calculate L2, the second list, we have to calculate I comma 525 into 3 to the power I minus 1, and this I is this mod 809, and this I is varying from right. Okay. So if you do so, then we will be getting like this. This is the L2 list, 0 comma 525, 1 comma 7 2 comma 328. So like this, if we continue, then 9 comma 511 dot dot dot, then we have 19 comma 644, 19 comma 644, this is okay, 19 comma 644 dot dot dot, and the last one is 28 comma 163. Okay, these two lists. So these two lists are sorted based on the L1 and L2. So among these two lists, we just try to get the match the endpoint. So this is the matching here. This is our y. So if this is our y, then that means this is our corresponding I j, and this is our I. So hence we get log of this 5 to 5 base 3 is basically 29 into 10 plus 19 mod 808. So this is basically 309. So this is basically our result we are looking for. We can verify this by just calculating 3 to the power 309 is basically congruent to 512 mod 809. Okay, so this is the Shanks method. Now we will talk about another method which is called Poly-Hellman. So basically okay, so Poly-Hellman method for solving the discrete log problem. So basically the idea is, so we know that our alpha, we need to find out alpha a such that a to the beta is a to the power alpha mod n. Okay. Now what is the order of alpha? Order of alpha is n, and a is between 0 to n minus 1. Now we choose this 0 to p minus 1 basically. Okay, and we choose this p minus 1 as n, and p is prime. So p minus 1 is composite. So if it's composite, it can be written as product of prime. So that is the fundamental theorem of arithmetic. So we must able to write this as a product of prime, p to the power I, c to the power I, where I is 1 to k. So here pi is a prime number. Okay. Okay, so now our objective is to find the A. A is basically log of beta base alpha mod of n. Okay. So now if we can compute A mod p to the power I, c to the power I, for all of this I, for all I, then one can apply the Chinese remainder theorem. Then we can apply Chinese remainder theorem to get the A mod n. So, that is the idea. So, to get so if we can find A mod p to the power pi to the power ci, then we can, by applying Chinese remainder theorem, we can get this. Okay, so now the question is how to get A mod p to the power c. So, that we have to find out. Okay, so now the question is how to compute A mod, say q to the power c, where q is a prime. Now, q to the power c, how to compute? Okay, so this is a question mark. Now, q to the power c divisible by n, but q to the power c plus 1 is not divisible by n. Okay. So, now to determine x equal to A mod q to the power c, where x is basically lies between q to the power c minus 1. So, that means q to the power c must divides A minus x. So, this implies x is basically so this implies A is basically x plus s q to the power c, where s is an integer. Okay. Now, we write x in terms of the radix q, represent x in radix q. So, how we can do that? So, we will write x to the power as it radix q, I mean we know the octal system, we know the decimal system. So, this is basically A0 plus A1 cube plus A2 q square like this. So, dot 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 A c minus 1 q to the power c minus 1. Okay. So, then basically A is basically x plus s q to the power c. Now, the question is how we can find this AIs. So, these AIs are unknown. So, AIs are unknown basically. So, 1, 2 up to q minus 1, these are unknown. Now, the question is how we can determine these AIs. So, to determine this AI, we need to use this we want to use this result like so, first of all how to compute A0. So, to compute A0, what we do? We claim this result. Claim is beta to the power n by q is equal to alpha to the power A0 n by q. So, this can be easily verified. So, basically beta to the power n by q is basically alpha to the power a n by q. So, now this is basically alpha to the power summation of a I q to the power I plus s q to the power c n by q. So, this will basically all terms will vanish mod n. So, we will only left a0 n by q. Okay. So, now if we take this gamma is equal to alpha to the power n by q, now we keep on calculating gamma square, gamma cube until gamma to the power I is equal to beta to the power n by q, and this is an exhaustive search for some I, and that I is basically our a0. So, if C1 is 1, so this is for all I, and that I is basically our a0. Okay. So, now once we have a0, we will keep on calculating, we will try to get a2, a3 like this. So, this is the way we try to get all the A's. So, once we have all the A's, then we got the a to the power, basically we got the x a mod q to the power c. So, once we have the a mod q to the power c, then we can have the we can apply the Chinese remainder theorem to get the a mod n. So, that is the general, that is the form of the Pauli-Hindman method. Thank you.